So, we have seen the equation f r double dot is equal to f external is valid for a system of particles. So, we can write the conservation of linear momentum if total external force is equal to 0. So, if f external is the total external force of a system of particle is equal to 0, then we see m r double dot, which is nothing but p double dot is equal to constant. P double dot is equal to 0, or sorry, p dot is equal to 0, which gives you p equal to constant. So, for a system of particle, conservation of linear momentum helps. Now, let us try to define angular momentum L for a system of particle. Now, angular momentum L, how will you define it? So, let us go back to this picture once again. See, angular momentum can be defined only with respect to some origin. In this case, this is the arbitrary origin we have chosen. We could have chosen it here also or here also, anywhere in this page, anywhere, okay, or inside in the middle of somewhere inside the system of particle. But let us say this is the origin. So, angular momentum L will be defined for a particle, for the ith particle will be defined by r I cross p I. P I being the linear momentum of the ith particle, p I is nothing but m I v I or m I r I dot, right. So, if I, so this is the ith particle. Now, if I try to define a total angular momentum, for a system of particle, which will be simply L I sum over I m I r I cross r I dot, right. So, this is the definition. Now, let us try to define a quantity. Let us say the force F I on ith particle. So, the force F I is acting on ith particle. If it is acting, when the force is acting, unless and until the force is in the same line as the, or unless and until the force is central in nature, that means it acts only along this radial vector itself, there is a external torque which is result, which is there due to the result of this external force F I, right. Sorry. Okay. Now, if we try to calculate this torque on the ith particle, which is given by n I simply is r I cross F I, that is the torque of this particular force on ith particle about the origin. Okay. So, like angular momentum, torque has to also has to be defined around a fixed origin. Unless and until we do that, it has no meaning. Actually, that is true for any quantity, even the position vector, the velocity, all has to be defined with respect to some origin. Okay. So, the total torque n on the system of particle will be sum over I n I, and it is given by sum over I r I cross F I, right. So, once again, if we try to define the total, if I try to write a relation including total torque and total angular momentum of system of particles, we have to remember that the force F I on ith particle also has an additional component, which is sum over j, which is not equal to I F I j, right. So, the torque, so this is the total force, actually not this is the external force which is acting on ith particle, and this is the total force. So, actually, so I am bit wrong here, so we have to consider total force. So, F total is has two components F I plus this. So, if we now try to estimate total torque, which will be given by I R I cross F I plus sum over j, which is not equal to I F I j, right. Now, if we compute this term now, this sum will go in. So, we can break it into two sum, one is R I cross F I being the external force on ith particle plus sum over I and j not equal to I R I cross F I j, right. Now, this F I j, as I said, we can always break it into the form F I j minus F j I. So, this can be done. Okay. Now, if I examine this sum, this particular sum, I will write it again, sum over I and j not equal to I R I cross F I j. So, essentially I am trying to calculate the torque due to internal forces. Now, this will have pairs like R I cross F I j plus R j cross F j I, because this indices I and j, they are interchangeable and they are identical, I mean they are exchangeable indices. So, we will have pairs like them. So, this particular term will give me pairs like this. So, this entire term can be broken into terms paired terms like this. Now, if I examine this particular term, F I j is equal to minus F j I. So, we can write F I j, okay, cross R I minus R j, and R I minus R j is nothing but, if I go back to this original picture of system of particle, R I minus R j is along this radial vector, along the vector which joins the particle I and j. Now, this F I j is a force which once again acts along the same line. So, if I look at the cross product, F I j is also a force which is acting along this line, and R I minus I j is either in this direction or in this direction, depending on how we define, I mean which one is I, which one is j, does not matter. If R I minus R j is along this direction or in that direction, thing is this cross product, irrespective of it is along or opposite to this particular direction, this cross product will unanimously vanish. So, that means the total torque N of a system of particle once again can be reduced to, so which was this two term, this term will be uniformly vanishing. So, it will be nothing but sum over I R I cross F I. Now, which if you remember this R I cross, okay. Now, R I cross F I, if I remember the first relation we wrote, okay, this sum over I F I can be represented by R I sorry. So, this is one relation, right. Now, there is a relation which connects this angular momentum at this total external torque with the angular momentum, and that relation for ith particle is R I cross F I, which is the torque of ith particle, is d dt of R I cross m I v I, which is the angular momentum of ith particle. Now, we know, we have already proven it during our discussion of central orbit, that this relation has to be valid for each of the individual particles of this system of particles. Now, if I run the summation over I in both sides, we immediately see the left hand side gives you the total external torque n, and the right hand side, this gives you, if the time derivative will come out, and this will give you the total angular momentum of the system of particles. So, the relation which we have derived for one individual particle, which we knew that it is true for one individual particle, holds true for the entire system of particle as well, and this is primarily because the torque due to the internal forces, all the entire torque due to internal forces actually vanishes, right. So, this is one important relation. So, we see that the Newton's second law, which relates the rate of change of momentum with external force, that is valid for a system of particle, as if the entire mass is concentrated at a particular point, which is called the center of mass of this system. And we have seen that the total external torque is also total external torque due to the external forces for a system of particle is equal to rate of change of angular momentum, right. Now, also what we can do is we can write a conservation principle for angular momentum. If we get n is equal to 0, that essentially means total torque due to all the external forces equal to 0, then that tells you that L is equal to constant. So, this is like linear angular momentum conservation. We have linear momentum conservation, we have an angular momentum conservation for the system of particles as well, right. Now, the next important topic is the motion with respect to center of mass. So far, we have considered a system where the center of mass is, so we have an origin which is somewhere here, and let us say that is where my system of particles belong, and this is my origin, and I have calculated the, so whatever calculation I have done it with respect to an arbitrary origin. Now, let us assume a situation where I am for each of this particle of this center of system of, for each of this particle in this system, I have two coordinates available. One is taken with respect to an arbitrary origin, which we have done already, and the second coordinate is with respect to the center of mass. Now, see what happens. So, this is my system of particles. Okay. So, this blue dot is my CM, right. So, for any particle here, let us say my, with respect to my arbitrary origin, please understand that center of mass is also defined with respect to this origin. Okay. So, the position vector is r I, and with respect to center of mass, the position vector is, let us say, r I prime, and capital R is the center of mass's coordinate. So, we can write r I is equal to r plus r I dashed. Okay. So, if I go by the definition of center of mass, which is sum over I m I r I, now put this value of r I in here, what we will get is sum over I m I r I prime plus r, right. Sorry, r sum over I m I. Now, the second term, this will simply give you the total mass of the particle. So, if you open the bracket, the first term will be 1 over m sum over I m I r I prime plus r. So, you see this from this equation what we can infer is sum over I m I r I prime is equal to 0. Also this, and if I take the time derivative of it, then the time derivative of position vector with respect to center of mass will give you the velocity. So, I can also write a relation that m I v I prime is equal to 0. So, this quantity is called the moment and this quantity is called the momentum. So, both moment and momentum for a system of particle with respect to the center of mass vanishes. This is a very important relation, we will be using it during our discussion of rigid dynamics a lot. Now, okay, so this one is not very intuitive, but this one is very intuitive. Think of a situation. Let us say you have a toy, toy explosive which actually explodes in the middle. I mean, so I think we all have this Diwali pataka, we have fun with it sometime. So, we have this explosive, small explosive, we put fire to it and throw it away. On the midway it explodes. Now, let us say it is moving with a particular velocity, right. Now, moment it explodes, the total force which due to which it explodes, it is an internal force, right. Now, because of this internal force, all the parts of it, they start moving in different directions. Now, consider the center of mass, consider this motion from a center of mass frame. From center of mass frame, the position vector of all the particles are changing constantly. Also the velocity is changing. Now, according to relation I have just derived, any particle which is of that, any piece of that explosive which is moving away from the center of mass with some velocity, some position vector r I and some velocity r I dot, okay, or which is given by V I, the total moment or total momentum calculated with respect to the center of mass must vanish, and this is in accordance with the conservation of linear momentum. So, for that particular piece of explosive, the total the total momentum which is carried away in all the directions will vanish. If you recall, during our discussion of systems with variable mass, we took up a problem which was like a raindrop is evaporating, a raindrop in free in vacuum is evaporating. So, let us say, and one of the basic assumption in solving this problem was the net momentum carried away in all the direction vanishes, and that is a very valid assumption given that the momentum is carried away in all directions uniformly. So, that is why the momentum change with respect to center of mass frame is 0. So, we have this have a formal proof for it. Now, let us move to the problem set. Once again we have a problem which is also related to this small derivation. For a system of particles, show that the total angular momentum about an arbitrary origin equals the angular momentum of the total mass located at center of mass plus the angular momentum about center of mass. So, essentially what we need to show is the total angular momentum L, which is L has two components. One is the angular momentum which is about center of mass, and the second is the angular momentum which is measured with respect to center of mass, right. So, essentially, sorry, I have made a mistake here. It will be R I prime. So, it will be R I prime V I prime. Okay, I will correct it in the final assignment, right. So, in order to prove this, let us look into this. R I is equal to R I prime plus capital R. So, V I will be equal to just the time derivative of this. So, V I prime plus capital V. So, L will be equal to sum over I m I r I cross v I. So, this is the definition of L we know. Now, we substitute r I with this relation. So, once we do that, we get m I r plus r I prime, and also we substitute the same for v, we get v I prime plus capital V. Capital V is the velocity of the center of mass. Now, if we open the brackets and do it term by term, the first term will be r cross V, second term will be m I r cross v I prime plus sum over I m I v cross r I r I prime cross v, that is from this term, and there will be an additional term m I r I prime cross v I prime. Now, the relation which we just proved, that the moments and momentum around center of mass vanishes, by that particular relation we can we can set these two terms equal to 0. Why? Because we can take m I inside this, and we can write it as r I cross sum over I m I v I prime, which is equal to 0. Similarly, this one can be written as sum over I m I r I prime cross v, capital V, which is once again equal to 0. So, what we are left with is, so these two quantities are I independent of I. So, we can execute this summation. So, this is m r cross v plus this additional term, which is sum over I m I r I prime cross v I prime. So, hence we have proved what we have to prove, and we will see later that this quantity itself will give us some interesting theorems of moments of inertia, but that comes later. Now, with this we formalize the discussion of systems of particle. Let us move into rigid body. Now, what is a rigid body? A rigid body is essentially a system of particle, but with a very specific property. For example, let us say this water bottle. Is it a rigid body? It is not, but because it is full of water, I mean there is some certain amount of water in it, and we cannot call it a rigid body. But if I somehow manage to drink this water, or I somehow drain this water, I have an empty bottle, that is a rigid body. What are the differences? The definition of rigid body is a system of particle where the relative separation between the points are fixed. So, now look at it again. When there are water molecules inside, we know that it is liquid, and in liquid the water molecules, the relative separation or relative position of liquid molecules changes. That means, when we have water inside this system, it does not qualify for a rigid body. Moment we drain the water out, it is a dry system, it is a solid bottle, it is a plastic material where the separation between this two particles, they are fixed. Again, plastic is also not a very good example of a rigid body. It is a polymer material. Polymer has certain properties which might not qualify for rigidity, but a metal object or a piece of wood, for example, and so even a piece of brick, these are very good examples of rigid body. Now, what are the terms we need to know about rigid body? There are two very important parameters in a rigid body, which we are going to discuss now. One is degrees of freedom, and the second one is constraints, right. Now, what is degrees of freedom? First of all, we have to understand, let's go by the formal definition. Degrees of freedom, we also call it DOF, is the number of or minimum number of independent parameters, or rather I will call it coordinates we need to describe a system. So, it is the minimum degree of freedom is the minimum number of independent coordinates we need to describe a system, and constraint is okay, there is in terms of, if I want to correlate this to, the best definition of constraint is the conditions that describes the reduction of degrees of freedom. Now, let us try to understand this one by one. First of all, degrees of freedom. Let us say if I have a free particle in space. Free particle means, okay, what is the definition of particle? First of all, particle means it is a point mass. It does not have any physical dimension. There is only a mass which is very, very tiny. For that particle, how many degrees of freedom do you need, or how many independent parameters do we need to specify this system completely? The answer is 3. If we can write x, y, z coordinate, we can write r theta phi coordinate, but if we know 3 coordinate parameters, 3 independent coordinate parameters for that particular particle, we know the position of it completely, we define the position of it completely in space. We have 2 particles independently moving, I mean, let us say they have no relation. So, we need 6 parameters. Now, in a system of particle, if there are n number of particle, capital N number of particle. So, in principle we need 3 times capital N number of parameters to describe the system completely, given that there is no relation between each 2 particle. But what happens in a rigid body? For rigid body, because there are so many constraint conditions, there is an additional constraint condition. So, if I try to formalize it, we need, for a n particle system, we need 3n number of DOF, degrees of freedom, or rather the degree of freedom of a system of n particle is 3n. But for a rigid body, what are the number of constraints we have? We have a number of constraint as NC2, or sorry, capital N C2 number of constraints, right. Constraint is the condition that describes the reduction of degree of freedom. For example, if we fix in a system of particle, if I go back to the original example, we have 2 particles, we need 6 independent parameters. If I now fix the length of this, if I fix the separation between these 2 particles, number of degrees of freedom needed to describe the system reduces. So, this is a constraint condition. When I fix the distance between these 2 or fix one particle, that means we immediately fix 3 parameters of it. So, even for a 2 particle system, we just need 3 independent parameters, because the first particle is not moving. So, that is the constraint condition. Now, for a system of n particles, for a rigid body, the reduction of constraint number of reduction of number of degrees of freedom due to number of constraint is not straightforward. We cannot just calculate it by this relation. So, let us say we need 3n number of degrees of freedom and NC2 number of constraint. So, we can simply say that the degree of freedom of a rigid body is 3n minus NC2, which is 3n minus n into n minus 2 by 2, but it is wrong. This is not right, because there are logical reasons for it. If you go through the master book of classical mechanics, that is Goldstein's book, you will have an idea why this relation is wrong. We are not going into this. So, today's class we are stopping here. In the next class, what we will do is we will first define the degrees of freedom of a rigid body, and we will continue from there. Thank you.